Okay, so today we're going to go over the ideal gas law. This is going to be on page M100. Since I don't exactly know where we're going to start and leave off before I go on maternity leave, we're just going to start and say all maternity leave pages will start with an M, and so we're going to call this one M100. And so if you look on Schoology, you should find your skeleton of notes for the ideal gas law for page M100. And so in order to get started with this, we first have to understand what an ideal gas is. And so we have to compare that to what a real gas is. And so we have 4 questions that we're going to answer. What is the difference between a real and ideal gas? What does the ideal gas law state? What is the mole to liter conversion based on the ideal gas law? And then how do you apply the ideal gas law to stoichiometry? So we're going to have 2 slides of notes. This will be our first slide, and then we have an additional slide that's going to go behind that. Okay, so let's just get started with what a real versus an ideal gas is. We know that gases are made up of atoms, and those atoms have volume and mass. But whenever we talk about an ideal gas, we don't account for their volume. So that's one of the first things we're going to write down, is that ideal, like perfect world gases, when we're talking about ideal gases, we do not account for the volume. Do not account for the volume of the particles. So we just pretty much ignore that the particles themselves have any volume or take up any space. We just ignore that. And the other part that we say is that we say when we have an ideal gas and those particles are bumping into each other, we call each collision an elastic collision, meaning they bump into each other and they bounce right off. There's no attractive force between particles, no repulsive force between particles. Well, we know that that's not really true. In the real world, there's going to be some sort of either attractive or repulsive force between those particles colliding. But when we talk about an ideal gas, this perfect world gas, we say that they're just like bouncy balls and they bounce off each other and move on. So we're going to write that down now. Ideal gases have elastic collisions with no attractions. Or with, we'll just call it no attractive forces. With no attractive forces. Okay, so that's the first thing that we need to be able to do. We need to be able to describe the difference between a real and an ideal gas. A real gas has volume of particles, but an ideal gas, we do not account for the volume of particles. When we're talking about the collisions between particles, ideal gases have elastic collisions with no attractive forces. That's the opposite when we're talking about a real gas. Okay, but this allows us to have the ideal gas law equation. And so the gas laws are a series of equations that allow us to talk about the pressure, the volume, and the temperature, and how all of those things are related for any one gas. And so we're going to start out with the ideal gas law because we've recently finished up stoichiometry, and that kind of all plays together. So for the ideal gas law, we call it Pervnert, which is PV equals nRT. PV equals nRT, and we're going to go through and talk about what each of those things means and how each of them plays a role in the overall equation. But we can see here that we've got P for pressure, V for volume, T for temperature, N is going to stand for the number of moles, and R is the gas law constant. And so we're going to kind of define all of those. So P is going to be pressure. And for what we're going to do, we're going to use that in ATMs. There are other options that you can do, but for us, we're just going to say ATMs. So that's P. P is for pressure in ATMs. For V, we have volume. Volume is going to be measured in liters. So remember, if we're given milliliters, we need to divide by 1,000 in order to get to liters. The N is the number of moles. N is the number of moles of the gas that we're talking about, and so we may have to do a gram to mole conversion. R, we'll write R over here. R is the gas law constant, and so it's always going to be the same number, and so our gas law constant is going to be 0.0821 L ATM MOL K. There's a fire engine running past us. I don't know if you can hear that. 0.0821 L ATM MOL K. And so we see in that unit that there's a liter for volume, the ATM for pressure, the mole for the number of moles, and so the K must refer to our last thing, which is going to be the temperature. And so T is the temperature, but it must be in Kelvin. And so you can see that this unit is always going to help us remember what we have to have for our individual units, because we've got the L, the ATM, the number of moles, and the temperature in K. So remember, when we're doing temperature in K, it's Celsius plus 273. Okay.